that's like these are all, so this, it's a pretty, even though it's not like, even though we haven't experimentally tested, because these strings are extremely small, like they're at the order of the Planck length, which I think from, so like just to give you an idea, from the Planck length to the atom length is like from an atom to the solar system. So that's just like the scale difference. So yeah, so these are really small, but, and also extra dimensions come out of this, and that's, extra dimensions have been a thought for a while. Okay, let's get to, so my idea, so right now my goal, and you could stay for, however you want, I'll try and speed this up, but my goal is just to replicate this procedure and then see what we get. I'll try and go.
Yeah. This might be kind of what Kojic was getting at earlier when he said set F equal to that. Is like you're saying that F is like the space, right? And then so these different strings would be like the
so
like
F is the space. So that's just so as P goes to infinity, this space just gets smaller and smaller. It gets more and more localized. The interaction.
Mm-hmm. I mean, like, I'm just thinking, like, you can maybe describe it a lot less explicitly, maybe.
Okay.
Right word.
Yeah. Okay. So I'll skip a lot. I'll finish up in like 15 minutes, if that's okay with you guys. Around it, that'll be good. So now for the point particle, we have the parameter tau, which is this is pretty much we have here the proper time, the distance in 4D space time. And for our string, we have the parameter tau and sigma. Okay, and sigma is just for a closed string, it goes from 0 to 2 pi. So it's just it just maps the edge of the string. So it gets information from every point of the string. So just like how the action, we have we said the distance, ds squared is just, dx mu. So we're gonna have here is this dx mu now has, so we're gonna add parameters. We're gonna say rather than tau and sigma, we're just gonna have just eta. So we have eta alpha, and alpha equals 1, 2. We have eta 1, eta 2. And eta 1 equals tau, eta 2 equals sigma. So now our dx mu is just d alpha x mu, d eta mu, and dx mu. Just say d beta mu is dx mu, or dx alpha equals d beta alpha. Okay? So now when we construct our world line, we get now instead of so we had the flat space-time metric here. So what we're going to get is d alpha x mu, d beta x mu, and then d alpha. So now we're going to have a new metric, which is called the induced metric. So if you guys, if all this notation is bothering you, so pretty much d alpha x is just d dt x, and we're going to denote that by x dot, just like how we did over there. X mu, we have d beta equals d x mu, d prime mu. Okay, so we have all these. So now we're going to so this is just the how the string changes in space-time, going through space-time, and this is how the string changes along its ring. So we're gonna say the string vibrates. So this is gonna be, so this d alpha, d sigma is just gonna model its vibrations, and we're gonna have just how we had creation and annihilation operators, raising and lowering operators. We're gonna have these operators which raise the vibration on the string and low. Yep.
So usually for a particle we have mass, so this will have a tension also in that string?
Yeah. So we're gonna construct an action very similar to that one. So but first I want you to define the induced metric. So this is gonna be the new metric we're gonna be working with. X squared, X top, AB. Squared. So this is going to be the new parameter we're working with. So just like how we had the action is just dt or d tau over mu nu dx dt dx mu dt. We're going to have the area function now because we're dealing with area, we're not just dealing with lines, we're dealing with proper area. We're gonna have that be gamma alpha beta, and then we're gonna have dx mu. Let me see. That's it's just So this is just our distance in this area. This is just the area, not the distance. This is the area. You have a question?
A little bit. So does x dot and x prime, do they commute?
I mean, no, they don't. Or yeah, they do. So they would equal 0. Like it's not dependent on each other. They're two separate quantities.
Just classical variables. Right?
Yeah, exactly.
Oh, okay.
Just coordinates.
Yeah, so this is a classical string, by the way. We're gonna quantize it next time.
Oh, okay.
Okay, so we're dealing with we're just constructing a classical version. So this actually just equals d sigma squared, and then that's just the square root of gamma, and gamma is just the determinant of gamma alpha beta. Okay, this is so the action itself is it's minus t. This is the Nambu-Gato action. So we had the action for a point particle as minus mc squared or minus mc ds. So we're gonna have this action, can you guys see? Be minus t d tau d sigma, and then the determinant of that. So when you take the determinant of this matrix, you get x dot squared, x prime squared, minus x dot times. So we're gonna have this in here. And when we solve the Euler-Lagrange equations, what we get is, we just get P equals minus T, so P mu tau. P, this is actually plus P sigma mu. So T is the same as mass, so T takes the form as mass. So the tension, so the string has a tension. So if you think about it, like any way, just a classical string has tension associated to it. So
This tension here, you have to introduce yourself, or it pops out from the formula?
well, okay, yeah. So it's so we introduce it. So it's a way of making string theory. It's a way of
It's a
making,
constant, right?
yeah, exactly. So what happens is, so when we take a string not moving through space-time, so it has no kinetic energy. So there's like a kinetic energy part, and they have a potential energy. Actually minus. So just like how the action has just kinetic minus potential. So we have, when we just because we could, so the reason why I was doing reparameterization of variance is because we could do the same thing for string theory. Except when we fix the gauge to be, the string is only moving through the time direction, then there's no kinetic energy, and then our potential energy is just VL, which is the length of the string, equals, or V, so V, our potential energy, is V equals the length of the string times the tension, or this constant T, and T equals the potential energy minus the length of the string, so it's just the potential energy per unit length of the string.
So what would happen to the string if you just no forces, you just let it go like a ring? It would just stay a ring forever, or it would try to collapse, or
Yeah, no, because there's this tension, so it's not gonna collapse.
so the tension goes plus and minus. Like if too small, it goes out. If it is too big, it brings it back.
Yeah, because it's an equilibrium,
Okay.
so it's stabilized.
The modes of this string, like how they vibrate, they will become the particles.
Yeah,
I know.
Like masses
But the thing
will-
is, how do you set that string? Is it like a spring which has certain, length which is natural, and if you extend, it comes back. If you squeeze, it goes back. Or is it always just, imploding force? So I guess this is just like a spring, right?
oh, yeah.
Yeah, probably imploding, yeah.
You think imploding? Yeah,
I
this.
think so, yeah, good.
Yeah, it has to, because then it wouldn't be, well, so the string could, okay, so what happens, like, this closed string, is it could detach, it could split, it could break. And, well, it has to live, so the whole picture, well, this comes into brains, but yeah, so pretty much a string could collapse, and then, which, I mean, it still has tension, like, it's still spread out. So the mass or the energy of the particle has to do with this tension.
Okay, so your action is really like the area of
Yeah,
the surface.
yes,
right?
exactly.
And now Lagrange other equations are looking for like which shape would minimize this area.
Mm-hmm.
And you think, well, the minimize is just a complete collapse. But this is in the space-time metric, so that's why
Yeah,
it
it's
is not,
metric,
the
yeah.
solution is not a collapse entirely.
Yeah.
It's going through some, right?
I think so, yeah.
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 Because it tries to go through the cone. The
Evolves.
cone will be zero, right?
Evolves, yeah.
But it doesn't want to also to extend, so it keeps it, so that's the trade-off.
Yeah.
Yeah, so this area might look, so this equation might look very unfamiliar to you. But before we leave, I want to state that this has very simple physics. So it's like, so if you take a film soap and you have it between two rings, the soap bubble between two rings, we could describe it using this functional, this area functional. So let's just take let's take gamma. So we have, this is a determinant. So for example, I'm just gonna do a very quick example. So if we have, this is x1, x2, this is L1, L2. There's like the area of this region. Now we could say that, so we parameterize it, eta 1, eta 2. We said equals to eta 1 lambda, or L1. So this length, and then x2, eta 1, eta 2, 2. So when we take the derivative, the first with eta 1, with x1, we just get L1, the derivative eta 2 with x1, we get 0, the derivative of eta 1 with x2, we get 0, and the derivative of eta 2 with x2, we just get L2. And then we already have it looking like this form. So we're gonna say eta runs from 0 to 1. It doesn't matter. This is it's invariant under our choice of eta, our specific choice. So we plug this back into the area equation, and we just get L1 squared, L2 squared minus 0, and that just gives us L1, L2, and that just gives us the area of this functional. So it's interesting. I do want to note here our Euler-Lagrange equation, as we saw it's just P mu T plus P sigma P mu sigma equals, and then the Lagrange, so the Lagrangian doesn't depend on X itself, so you know, we could just even say this X mu, which that just goes to 0. So once you solve the Euler-Lagrange equation, you get T X double dot minus sign T X prime prime equals 0. And then that just takes the form, this takes the shape of d dt squared minus d sigma squared x mu toss sigma equals 0. And that's just a Klein-Gordon. That takes the form of the Klein-Gordon equation. So what we could do now, and we saw how to quantize fields that obey the Klein-Gordon equation. So we could do now, we could just treat this string as a field on a sheet, on an area, on a world sheet, and then we could apply similar quantization procedure. So yeah, is there any questions? This is it. Just any general questions? And we're gonna see next time how once we quantize it.
But isn't it true that string theory requires what is that called? Supersymmetric particles?
Yeah.
And isn't supersymmetry ruled out by the CERN as of today?
I mean, it still hasn't been found by CERN.
I thought it was reasonably, or most of the physicists think there are no more supersymmetric particles.
But do you
True
I think
that.
I read a similar article, just a random article on somewhere recently.
If it was, or put it
Yeah,
like this,
no.
there was a bet held by, who was it? Who were the two people? I think
Well,
two.
Typical Hawking could be somebody that is right.
Hawking and Penrose,
They were
there's like-
betting every week or something, but something else.
And
you know,
who-
black holes.
accepted that probably supersymmetry will not be
found.
Which my question was, how does string theory work then? Like, so isn't it very critical for it?
Yeah, so it's so yeah, I guess, well, I mean, we're not gonna get into, I guess we could get into supersymmetry, but yeah, I thought they're still looking for superparticle supersymmetry.
Yeah, you know this guy Wilczek or Wilczek, you say?
But
Frank
then-
Wilczek? He's a proponent of supersymmetry, and he claims that if you go with the energy, to the higher and higher and higher, all the forces actually they meet pretty precisely at one point, while with any other theory they don't, right? There's no way to see that they're becoming one force. He
Including
claims that-
gravity?
Especially gravity.
So it's like a super gravity.
But I don't know what's the theory behind this. He just cheerfully announced it.
Yeah, every theoretician loves the idea. Supersymmetry is kind of so elegant that everyone likes it.
Maybe it is a quantum state that it is true and untrue.
Yeah, but so right now we're gonna deal with bosonic okay, so we might get into supersymmetry depending, I don't know, well, we didn't get to a good portion of what I want to cover, but, yeah, so right now, so we're gonna see next time when we quantize the string that in order for the theory to hold true, we need 26 dimensions. So we're gonna generalize this three-dimensional space into d dimensions, and we're gonna solve for how many dimensions are required, and it's gonna be 26. With supersymmetry,
Will you explain why 26? Using
well,
what's the argument?
okay, so you
No,
use
not now, but
it's
next
zero.
time.
Yeah, so it's zero. So it has to do with quantum fluctuations, the 0-point energy of the string. And then no, okay, well, yeah, we'll talk about it. But yeah, 'cause then, okay, so it's actually it's like really nice mathematics how 26 dimensions comes out. Like you apply the Riemann zeta function at -1, where if you have like 1 plus 1 plus 1, 1 plus 2 plus 3 plus 4 plus 5, you get this. If you sum that up, you get -1/12. So
on a good day.
And like in some, I don't know, is that some special case in mathematics that holds true, or holds true for just our normal?
Mathematics, yeah, well, in periodic, it's about periodic arithmetics, they define it normal. It's summation and others like that. But 26th dimension, I think it pops up in other investigations, not even related to string theory, is that right?
Yeah, so
Something-
extra dimensions is like, I mean, that's like, it's even if you're just like a particle physicist, it seems like, if you're not, even if you reject string theory,